Hello everyone, my name is Girimukundan Kumar from the Advanced Control Systems Lab at Virginia Tech, and I'd like to present a two-layer model reference adaptive control for uncertain hybrid dynamical systems. Let's start with a bit of background. This paper presents a model reference adaptive control system for nonlinear time-varying hybrid dynamical plans affected by parametric and match uncertainties, as well as uncertainties in the plan's resetting events and resetting time. The features of the proposed control system are as follows. It accounts for parametric uncertainties. It accounts for uncertainties in the mapping between resetting events, the plan and the plan's dynamics. It leverages a two-layer architecture by providing an auxiliary aerodynamic model for faster convergence to the reference trajectory. It introduces resetting events in the reference model and the auxiliary model to improve the tracking performance while retaining the reference model's overall behavior. We have prepared a numerical simulation that showcases the abilities of our two-layer hybrid architecture. This numerical example shows the dynamics of a disk to track a user-defined trajectory in a maze. The trajectory is unfeasible and intersects the boundaries of the maze. The disk is subject to elastic bounces each time it hits the boundaries of this maze. We then compare the performance of the proposed control architecture with an alternative MRAC-based framework that does not leverage the two-layer architecture, but is able to account for the plan's hybrid nature. We then compare the performance of the proposed control architecture with classical MRAC. The next video shows the performance of the proposed control system with two-layer hybrid architecture. Here we can see the maze represented by the solid pink and green lines. The dotted pink line represents the reference trajectory given out by the classical MRAC system. P user is the unfeasible user-defined trajectory. The dotted red line is the reference trajectory given by our two-layer hybrid dynamical system, and the solid black line is the actual trajectory of the moving disk. Here we can see the ball moving. It hits the boundary and has an elastic bounce, and this resetting event is taken care of by a hybrid architecture. You can also see that the user-defined trajectory is unfeasible as it crosses the boundary of the maze. Here we can see some more resetting events. Here we notice that the first two resetting events are not the right resetting events. So we are not having a good convergence to the user-defined trajectory. But the hybrid system recovers and we complete the task. The next video shows the performance of the control system proposed by Dr. Lafleto in his paper, Model Reference Adaptive Control for Nonlinear Time-Varying Hybrid Dynamical Systems, published in the International Journal of Adaptive Control and Signal Processing. The maze is set up the same way, with the outer boundaries represented by solid pink lines, with the inner boundaries represented by solid green lines. The solid black line represents the actual trajectory of the disk. The dotted red line represents the reference trajectory of the hybrid system. The dotted pink line represents the reference trajectory given out by the classical MRAC system. While finally, the dotted blue line represents the unfeasible user-defined trajectory. The next video shows the performance of a control system based on the classical model reference adaptive control architecture. From the simulations, we can see that the two-layer controller for hybrid dynamical systems allows the disk to follow the user-defined trajectory more closely despite obstacles, its dynamically unfeasible nature, and also the dynamically unfeasible user-defined trajectory. From the other two techniques, we can also state that the disk is not able to perform the same task as well. Although the proposed control technique is not aimed at trajectory planning and should not be used in favor of careless trajectory planning, it does provide an approach to merge open-loop trajectory planning and closed-loop control. Thanks for watching, and for additional information you can see the paper listed here, and also email Dr. Laflido at this email. Thank you.